All right, so as we jump right into Unit 8, which is all about applications of integrals, we're going to start by talking about what an integral represents. Yes, an integral represents net area under a curve, but we're going to dive a little bit more into that today. So I want to start with something familiar, and it says, what does each expression represent? So this one should look familiar. We know, I think based on our work in the last few months, that the net area under the velocity gives us the displacement of a particle. Now, I'm going to get there a different way, or I'm going to kind of show my work, but we know the answer is displacement. But let's go through and pretend we don't. If we're looking at this as the integral that it is, we would start by saying, okay, well, how do we evaluate this? We would take the antiderivative, which is position, and we would evaluate it from A to B. And so we'd go plug in our B, and we'd go plug in our A. And then mathematically, we would just find the answer, and we'd get a number. But I don't want to think about it as mathematically and finding a number. We don't have one. I want us to look at this as, oh, this is our ending position. This is our starting position, right? The position at the end of time, the position at the beginning of time. And so, oh, yeah, that's the change in position, which we do have a word for that. We said change in position is displacement. And that's not wrong, but today I really want us to focus on using this phrase. It's that we're finding the change in the position. When you integrate the velocity, you're finding the change in its antiderivative, okay? In fact, let's kind of look at it a different way as well. What if instead I write this as the integral of s prime of t? Right, so I'm kind of building something this way instead of this way. Right, velocity is the derivative of position, or I could even go in and put that into words. Right, I'm asking you to integrate the derivative of position, or I'm going to write the rate of change of position. That's a horrible pen. Sorry, I won't use that one again. And the reason I'm writing it this way is because now we can look at it and say, well, an integral tells us to take the antiderivative. The word rate is telling us to take the derivative. Those two things are undoers, leaving us with the phrase change of or change in position. So, I mean, I got there two different ways, and I like this way. Obviously, they both work. Again, we should have known this from our work already this year. Okay. Now this next one though is not something I've said memorize what this means, right? We're going to build it the same way we just did the last one. Two ways actually. We could look at it as, oh, evaluate the integral. Take the antiderivative and evaluate it from A to B, which would give us the velocity at B minus the velocity at A, which represents the difference in or the change in the velocity over time. And we don't have a word for that, right? Displacement is very specific to meaning the change in position. But the change in velocity, we don't have a word for that. So, okay, fine. But what this value would represent, whatever we get for this answer, it would tell us how much the velocity increased or decreased over that time period. But just like we did that, the last one, we can go in a little bit differently and say, well, we are integrating the derivative of acceleration. I'm sorry, we are integrating the derivative of velocity. We are integrating the acceleration. And if I put that into words, v prime of t, the derivative of v, is the rate of change of velocity. Just putting that into words. And again, the integral tells us to take the antiderivative. The word rate means derivative, leaving me with that phrase, oh, change in velocity. The deal for us is that when you are integrating a derivative of something, when you're integrating a rate function, you're finding the change in the original function, right? So We actually call this the net change theorem or the total change theorem. And all it says is when you integrate a rate, your answer represents the change in the original. Okay? So I just kind of put that a little more out of context, right? A little more more generally. I didn't use particle motion, but I said if you find the area under the derivative, that answer represents the change in f, the change in the y values. Let's just write that down. Okay. Now, this should look familiar, I mean, based on our work back here, but even to me, this looks like the fundamental theorem of calculus part 2, saying how do you evaluate an integral? You take its antiderivative and you plug in the bounds. But we're just looking at this answer as a difference in two y's. Yes, it still represents the area under the derivative. It's just looking at it a different way. And so what I'd like to do is rearrange this equation, right? Here's my equal sign. I have two terms over here. I'd like to take this term and I'd like to move it to the other side of the equal sign, right? So I'm going to add f of a over there. That's all I'm going to do, though. Everything else stays the same. And I'm doing this for a reason. I'm doing this so we can maybe kind of interpret this expression or use it a little bit differently. So we know f of b means the y value at the end. We know f of a means the y value at the beginning. I just moved it around. So let's kind of label these things. This is what I'm going to call the initial y value, right? The y value at time a. Plus, now we've just said up here that this integral represents the change in the y values, and that will equal your new or final y value. And to me, rearranging this is not creating a new formula for us. I think it's actually pretty common sense. If you know where you start and you know how far you move, then you know where you end up. Or we could rephrase it, if you know how much money you start with, and then you know how much money you add or subtract from your account, then you know how much you have left, right? So we're going to continue to use this a lot. I'm going to say initial plus change equals new. This is a really big deal for us in solving some different types of questions, okay? All right. So let's take a look at this first question. By the way, this unit is going to be very calculator heavy, so I have my 84 sitting here. I'm just going to pop in and make sure it's in radians, which it is. And we'll use kind of calculators along the way. It says a population of insects increases at a rate, it's in bold, but I like to circle it anyways, given by this quadratic function. And that rate function is measured in insects per day. By how many insects did the population grow during the first 3 days? So I'm asking essentially to find the change in the population, right? Did it increase? Well, I know it increases, right? But by how much did it increase? What's the change in the population, okay? And so, that goes back up to here. If you want to find the change in something, you want to integrate its derivative or integrate its rate. So, that's good because that's exactly what I have. So when I integrate that function r of t from 0 to 3, that's going to give me the change in the population. So I see I have two questions about this particular function. So I'm going to go ahead and take this function and put it into my y1 just to maybe save a little bit of time later. Perfect. So I'm just going to go in, I'm going to hit Math 9. I know that's kind of dark. I'm going to integrate from 0 to 3, my function that's in y1, dx. And so my population grew by 647 1/4. We were not told otherwise about rounding, so we're always going to go to that third decimal place. Okay. So then the next question says, find the insect population after 10 days, so notice my time has changed, given that there are 35 insects at time 0. So essentially I'm saying the population at time 0 is 35, find the population at time 10. I just kind of made up a name of that function, P for population. Right, well, let's go back up here. Your initial population plus the change in the population equals the new population. So I'm going to go write that down, just kind of generically. The initial population plus the change in the population equals the new population. Perfect. My initial population is 35. We just talked about how to find the change in the population. Now the time frame has changed. So instead of integrating from 0 to 3, I'm going to integrate from 0 to 10, but the function stays the same. And that's going to give me my final population. So 35 plus the integral from now 0 to 10 of that function that I put in y1 to save the def for later. And I get 2,618 and a third. Again, I know it seems silly to talk about a third of an insect, but no one told us otherwise, so we're going to round to the nearest thousandth. Okay. Good. Let's take a look at the next one. So this says f of 3 equals 7, and f prime of x is 1 over the square root of 1 plus x squared. Find f of 6. So I am going to go back up here real quick, and I'm going to grab a couple of little kind of highlighter pens. I do want to point out before we do this question, this is kind of important. If this x value is a, then I'm going to start my integral at a. And if I'm trying to end at an x value of b, then I'm going to end my integral at b. So if you're trying to get from an x value of a to b, your integral must go from a to b. And I can go back here and talk about it on this one. I was trying to get from a time of 0 to a time of 10, so I integrated from 0 to 10. Now, this one has no context to it, and that's okay. Right, but they're giving me f of 3 equals 7, and they want me to find f of 6. Well, to me that's saying, oh, you have an initial y value plus the change in the y value equals your new y value. And let's talk about this for a second. Sometimes we think initial means time of 0. Well, I don't have a time of 0, but what I do know is something that's going on at time 3, and I'm trying to end when time is 6. I don't know why I just said time. These are x's. I guess I should change that, but same kind of idea. So my initial y value is 7. That's at time 3, or x equals 3. And I want to find the change in the y value. And to find the change in y, we integrate its derivative, which we were given the derivative, weren't we? And we're trying to get from 3 to 6, so we're going to integrate from 3 to 6. Now, this is not something we can do without a calculator. In fact, that's kind of how we started class, and I didn't start the lesson here this way. We can't integrate this by hand. We don't know the antiderivative of that. It's kind of like why we needed a new method. This is a question I could have asked in January if this were a different function. But if we can't take the antiderivative, this is the only method that's going to work for us. So I've got my 7 out front. I know that's a little blurry. Plus the integral from 3 to 6. And then we've got our lovely fraction 1 over the square root of 1 plus x squared dx. Okay. So very common theme today. Initial plus change equals new. If you know where you start, and you have your derivative, you can integrate to find your kind of where you end up. Good. All right, let's flip it over. All right, so this one says a particle travels along a vertical path with its velocity in meters per second given by this lovely velocity function. Products, compositions, trig, lots of good stuff in there. And the particle's position is 4 when time is 1. I just kind of like seeing that written a little bit differently. The position at 1 is 4. All right, I've got my calculator handy. In fact, as I talk, I'm going to probably get this typed into my Y1. But we've got 3 questions here. Number 1 says, find the total distance traveled by the particle in the first 5 seconds. So again, as I'm talking, I'm typing this in to my Y1, just so I have it. Of course, we have to use X's, right? Honestly, this first question is not a new question. This is an old question, but I threw it in there for fun. Total distance is found by looking at the total area under velocity. Right, we already reviewed displacement. That was the first thing we talked about today. That's the net area under the velocity. And if you want to find the total area, we said, well, you first need to make your velocity function positive, and then you can calculate the area from 0 to 5. Right, so that's an old question for us. I'm making sure I'm in radians. I thought, yep, I did that already. And so I'm going to hit Math 9. We're going to go from 0 to 5. I'm going to grab my absolute value of y1 and get out to the end there and get my dx. And it might take a minute, and that's okay. So I might set that aside if it doesn't pop up here and come back to that. All right, fine. It's taken a while. It's just the answer, right? The answer is not as a big deal to us. It's still going. So let's take a look at part B. It's not labeled that way. This one says find the particle's position at time 3. So I know the position of the particle at time 1. I would like to find the position at time 3. I'm thinking, oh, initial position plus change in position equals new position. And you will not believe it, this answer finally just popped up like 4 seconds ago. So if you're interested, sorry to interrupt, the answer to that one is 27.380 or 381. Okay, sorry. All right, so let's jot down a few notes. The position I have right now is at time 1. The position I'm trying to find is at time 3, which means when I go to find my change in position, I'm going to integrate from 1 to 3. All right, so my initial position is 4. To find the change in position, I want to integrate the velocity, which is this function, but I'm just going to write v of t, and we're going to go from 1 to 3. Now this one should go much faster on my calculator because I won't have absolute values around it. So I have 4 plus the integral, I have 9, from 1 to 3, of course, and then I've got my function y1 dx. Perfect. 3.536. And just like always, it's less about the answer for me right now as it is for just writing down how we come up with that answer. Okay. All right, so we just found the particle's position when time was 3. But let's say perhaps I wanted the position when time is 4. Well, that means we're just going to change this upper bound to a 4. Or if I wanted to find the position when time is 7.5, we would change that to a 7.5. If I wanted the position when time is 19, I'd change that upper bound to a 19, but nothing else is going to change. The reason I'm bringing that up is because when I go to look at this next question, it says write a function for the position that works for any time, right? We can't take the antiderivative of this. I mean, think about it. Products, U substitution won't help. Integration by I don't want to talk about this too much, but we can't take the antiderivative by hand. So the only option we have is to use what we just did. Except we're not going to put a number there. We're going to put a generic time up there. So the position can be found by using this formula here. My initial position plus the change in position from 1 to whatever time I want. Now time out. If I put a t up here, I can't use a t down here, can I? So we're just going to temporarily change that variable to anything you want. You can use a theta, you can use a u, I used an x. We had that conversation back in January, that if you have a variable in the bound of your integral, you can't use that same variable here. So you have to temporarily change that, just temporarily. It doesn't change anything about the graph, right? We've always said sine of x looks just like sine of t, looks just like sine of theta. So we're not changing the math, we're just changing the name of the x-axis. right? But here's why we need to do that as a reminder. If I said then, I want the position when time is 5, then that would tell us to go put a 5 in for every t. And if these were t's, well, then we'd be putting the t into more places than we want. We only want to put the number up here. That's why we change that. Okay. All right, let's take a look at the next one. So it says water flows in and out of a storage tank. A graph of the rate of change of the volume of water in the tank in liters per day is shown. So you can't really tell, that's a little r, but I'm just going to write this is the rate of change of the volume. If the amount of water in the tank at time 0 is 25,000 liters, estimate the amount of water in the tank after 4 days using a midpoint Riemann sum with 4 equally spaced intervals. Wow, there's a lot going on there. Here's the thing. They gave us the initial volume, and they want the new or final volume, right? Estimate the amount of water in the tank. Well, we've been saying now for like 20 minutes, the initial volume plus the change in the volume equals the new volume. And the initial is at time 0. The new volume is after 4 days. Well, look at that. My graph does go out to 4 and stop. All right. Well, my initial volume is 25,000 liters. Then I want to find the change in the volume. Oh, we said if you want to find change, you need to integrate the rate of change of the volume. Oh, well, look at that. Let's then integrate that function they gave us from 0 to 4. Now, this is different from the last few. We don't have an equation. We don't have a calculator, but that's okay. They told us exactly how to evaluate this. We're going to estimate, because that's the only thing we can do, the value of this integral using 4 rectangles. 1, 2, 3, 4. Now remember, an integral means net area under the curve of R, right? So look at this, part of this goes below. That's okay. They said water flows in and out, so I'm okay that the rate becomes negative. That just means the volume is decreasing. In fact, I'm going to jot that down. When my rate of change of volume is positive, that just means the volume is increasing. And when the rate of change of volume is negative, that just means that the volume is decreasing. That's okay. They said water goes in and out, so I'm okay that the rate is negative. All right, so I'm going from 0 to 4 with 4 equally spaced subintervals, which is great. That just means each one has a base of 1. I'm running out of colors here. That's okay. And they want us to use a midpoint Riemann sum. So my first rectangle sits between 0 and 1. In the middle, I go up until I hit the curve, and there's the height of my first rectangle. Looks like it's at 1,500. So the base is 1, the height is 1,500, so the area is 1,500. My second rectangle has a base of 1. I go to the middle, up, 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 up until I hit the curve. I have to eyeball that height. Let's take a look here. Let's see if that's 1,500. Let's call it 1,800. Might look like a little bit more than half. We're eyeballing it. You might have a different number than I do. My third rectangle, I go up until I hit the middle there, or I go up in the middle until I hit the curve. Let's call that 1 by 750. And let's do our last one here. This one has a base of 1, and I go to the middle. I go down, down, down until I hit the curve. And that's the height of my last rectangle. Now, it's negative because it's below the x-axis. You know what? I'm going to do myself a favor. I'm just going to say that it's about 750, right? Looks like it's about the same height as that last one. Okay. And so I don't even need to grab a calculator, but so we're going to take our initial value, and then we added 1,500 liters, we added 1,800 liters, and then those kind of cancel each other out to get our grand total of whatever that is, okay, in liters. Okay. So let's finish up with this question here. It says the tide removes sand from Sandy Point Beach at a rate modeled by this lovely function. So I'm kind of peeking at my calculator here thinking I should probably get this typed in at some point. So the tide removes the sand. I'm just going to write that down. Rate of removal. Like on the last one, water was leaving the tank. We were removing water from the tank. Okay, come back to that. Then they just give us a little more description. R of T is measured in cubic yards per hour. T is measured in hours and is valid for time 0 to 6. At time 0, the beach contains 2,500 cubic yards of sand. So that's my initial amount of sand. The question is, how much sand is on the beach at time 4? Oh, all right, well, it's what we've been doing forever. Initial amount plus change in the amount equals the new amount. Oh, okay, great. Now, real quick, let's just kind of think about this for a moment. We are starting with 2,500 cubic yards of sand. That's the amount at time 0. If the tide is removing sand, then after 4 hours, I think our new amount should be less than 2,500. Right? Keep that in mind. Because what I'm going to do, I'm graphing this. Actually, we'll put our calculator right over here. 2 plus 5 sine of 4 pi x over 25. They said that this graph was valid from time 0 to 6. And I'm just using my trig stuff that the midline's at 2. I don't know, I'm going to go from like 0 to 7. Okay. This right here is the graph of the rate of removal. And I'm just going to come over here and just sketch it, if that's okay. From 0 to 6, above the x-axis. Which means if we integrate that function, that would be a positive value. So if we add that, we're going to get more sand than we started with. It doesn't make sense. This last one, when we were losing water, the graph went below the x-axis. Here, this rate is above the x-axis. We need to be in charge of physically removing the amount. So where we wrote plus the change in the amount, we're actually going to need to subtract. The rate is positive, so we need to subtract. We need to deal with the remove part. Let's see, we started at time 0, we're trying to get to time 4, so I'm going to integrate from 0 to 4. So that's just kind of what I wanted to end with, is if we're talking about removing something, we're going to need to really pay attention to how that graph is working for us, right? We need to subtract. So I've got my 2,500, I thought, minus the integral from 0 to 6 of that function that's in y1. And good news for us, it is less than that 2,500. So we did lose the sand that we were expecting to lose. And so my final answer is 2,468.184 cubic yards. Right, it's an amount of sand. The rate is in cubic yards per hour, but the amount of sand would just be in cubic yards. Okay, and then just the last thing, I just kind of put those two really important pieces of information just here as a summary, but nothing we haven't already written down.